Hi everyone. I seem to have recovered to the point where I can record tutorials again. So I wanted to jump back in with the video here. So I'm going to lead you through a couple steps. Firstly, I'm going to run the r.watershed tool. And then I'm going to introduce you to this kind of cool and kind of troublesome model builder aspect of QGIS. I'll show you how to use it to build a simple model, and then I'll talk a little bit about its strengths and weaknesses and where it should be applied and where it's more trouble than it's worth. And Going from there, I'm going to lead you through a little bit of this pretty simple land cover change analysis that we're going to be doing to complete this module. So to start, I'm just going to run the r.watershed. Oops, got to click over here. Okay, got to run the r.watershed tool. And um, the exact same parameters that I was giving you guys. So I'm going to say 5,000 pixels for our minimum basin size. And then I don't want most of these outputs. In fact, I'm going to keep it really simple here. I'm going to get the streams and I don't need the basins. Um, the drainage direction or flow direction, that's all. Just those two. Okay. Dot files. Oh, it's mad at me because I didn't tell it where to save them. Okay, fine. Um, this was flow direction. And okay, there we go. So the r.watershed tool, as you gathered from um, my description of it in the text, it's something I'm very familiar with. It is the simplest to use and most powerful watershed analysis tool out there. And it's also incredibly computationally efficient. I'm running this on the virtual machine right now, which is not a fast computer, and took it about 10 seconds there. So let's take a look. Firstly, if we just look at the streams, sort of funny to me that r.watershed produces the stream output as a raster. If I was giving you a quiz and I asked you how to represent a stream network, I hope you would say that's clearly vector data. Streams are lines. Um, but here it is, it's a raster. And of course, we could change it to a vector, but we're not going to do that just yet. Then the only other thing I got is this flow direction, just sort of a goofy looking map here. The value associated with each pixel in here um, tells us its flow direction. Um, and there's 8 possible directions because there's 8 pixels adjacent to every 1 pixel. Um, and the negative values they arise from the same issue as the negative um, upstream accumulated area values, but we don't have that problem within this basin. Okay, so let's just leave it on the streams layer. And then we want to set ourselves up to ask a question about land cover change and resulting changes in the stream. Um, and in order to do that, we need to be able to very quickly get the GIS to tell us what the watershed area associated with any particular location is. And there's this handy tool that can do that. It's a grass tool as well. It's called r.water.outlet. So if I open that up, it asks me 2 things. Firstly, it needs the name of the input raster map. Importantly, that is the flow direction map. Otherwise, it won't know what to do. And then it wants to know the coordinates of the outlet point. Um, Typing in the coordinates would be a huge pain. So we're just going to click on the little dots over here and just zoom in enough that I'm confident I'm clicking on a stream pixel. Click there. I won't save this as a permanent output for now. I just want to demonstrate what it does. Go ahead and run that. Okay. If I change the order so the streams are on top, there we go. It looks like it worked. I mean, it's if this yellow blob is the watershed basin associated with that one point, well, it looks pretty convincing to me. Um, of course, it's coming from the same tool set that generated this stream data, so it should be in agreement. But I can tell you from experience, these are pretty good tools when you have a good quality DEM and when you're working in a steep, rugged, high relief mountainous area. These tools tend to be quite accurate. Um, okay, so that's cool. We can identify the area that drains to any particular point. But there's sort of a nuanced addition to that question that I've encountered a lot in my work as a hydrologist and a freshwater scientist, and that is, imagine we're studying water quality along. I think we're on the, oops, yeah, all the stream names get terrible here. I think this is the middle fork of the west fork of the Gallatin. Um, I don't know. Surely they could find some rich people to name them after, but they haven't done that yet. Um, So if you're studying water quality along this stream here, you might want to know why the water quality is changing. For example, like just suppose in this um, purple reach, suppose that partway down this purple reach, you notice all of a sudden that there's maybe a lot more sediment coming in, or maybe a lot more nitrate coming in, or for some reason the water quality is degrading across that reach. And in order to understand that in the watershed context, you might want to ask the question, what is the area that drains specifically to this reach? Not just the whole area draining up to that point, but the area that drains in specifically to this purple reach. Um, and if you had poked around with all the outputs of the r.watershed tool, it does actually show you the basins associated with each of these reaches. Um, but I'm going to show you a way to do it that's a little bit more flexible. The the streams from the r.watershed tool, the length of a stream is just defined by, or like the unit of a stream segment is defined by these tributary junctions. So from this junction to this junction is a stream segment. Well, suppose we really just wanted to look at a change in the bottom half of this stream segment, right? Um, so I'm going to run r.water.outlet again. Flow direction is my raster, and I'll just click, say, somewhere around here. Say that's the top of the area that we're looking at. Run that. Oh, great, they're the same color. We better change the color of one of them. Um, we'll make it blue. Okay, so now, and you don't have to do all these steps just yet. I'm just sort of giving you an understanding of where we're going. So now, just based on those 2 points that I clicked on in order to run the r.water outlet tool twice, I've identified 2 areas. Firstly, I've identified the yellow area, which is the whole area draining to the bottom of the breach. And then I've identified the blue area, which is the area that drains to the top of the reach. And so logically, the area that contributes water along the length of that reach must be this area that is in the yellow but is not in the blue. This is starting to look a lot like some of the questions that we were asking with the Idaho wildlife analysis. So we could, we can take the exact same approach as we did in the last module. We could turn both of these basins into vectors, um, and then we could find the difference between one and the other, and that would tell us the area that drains specifically to one reach. But if we wanted to apply or if we wanted to ask that question across a whole lot of different areas, we'd spend a lot of time clicking around, clicking on buttons, waiting a minute for this tool to run, waiting a minute for that tool to run. And so if you were doing that, you might wonder if there's a way to combine these tools, and instead of running them all individually, waiting for the output and then running the next one, if you could just like build a chain of them and run the whole chain. And in fact, you can. And I will say there's similar functionality in ArcGIS, and it has similar strengths and weaknesses. So uh, that option is called the Graphical Modeler. I'm going to clean up my workspace here a little bit before I jump into that. Just remove these temporary layers. Um, and the Graphical Modeler is great for reasonably simple tasks, but um, when you try to build anything really extraordinarily complicated in the Graphical Modeler, it almost inevitably you run into some silly little issue that you just can't resolve. And you can definitely sink a lot of time into trying to get really complex models running in the Graphical Modeler. And so my advice is to identify simple bite-sized pieces, combinations of 5 or 6 tools that you can build into a model that's easy to understand and, if necessary, that's easy to debug or to fix. And if you're trying to do something more complex than that, either build a combination of graphical modeler tools that you can use separately, and that way you can verify that things are working along the way. And in doing that, maybe you've simplified your analysis down from 50 steps to 5 different steps, each of which uses a model that consists of those 10 intermediate steps. And it's also, the context for the limitations on this are that if you're really going forward and trying to do repeatable GIS analyses, you're going to end up getting comfortable with Python or R or another language that can be used to script these GIS processes. And so there's not really, from the developer perspective, there's not a lot of reason to make the graphical modeler, absolutely super incredibly powerful, because the real power users of GIS are going to end up, and that I'm sure will include many of you, are going to end up taking all the concepts and all the ideas and then actually scripting the analysis, because it does, in truth, it gives you better control over what's happening. But the graphical modeler it's easy to use, and it's a great introduction to this whole idea of building sort of like a meta tool, a tool of tools. So if I can, so we have 2 tabs over here. We have inputs and algorithms. Um, Inputs are the parameters that the final model will ask for, and then algorithms are the same list of tools that are available in QGIS. And so I do want you guys to follow along for this part. I do want you to build this same simple model that I'm building. So um, we're going to do it sort of one part at a time. Firstly, we're going to build a simple model that takes one single point input, runs the R dot water outlet tool on that point, determines the area associated with it, and then turns that into a vector. So just a couple steps. Then we're going to actually just make a copy of that, and we're going to have it require a different input point. That'll be one of them will be the lower extent of the reach of interest, and the other will be the upper extent of the reach of interest. And then finally, we're going to take the outputs from those two sets of tools, and we're going to use the vector overlay tools to find the difference between them, and that will be the overall output for our model. So what are the inputs? What are the parameters that you need to define in order to run this whole model, this whole set of tools that I'm describing? Well, we need three things. Firstly, we need a raster, and it needs to be the flow direction. That's because the r.watershed tool will need that. Okay, so I just created an input. I called it flow direction. And when I create an input, when you run the tool now, because I told it this tool needs a raster layer called flow direction, it's going to ask you to input the flow direction raster. In fact, I should be even clearer. Not that flow direction could reasonably be a vector, but flow direction raster. Okay. And then we're going to need 2 points. One of them is upper end of target reach. Okay. And the other one is lower. Okay. So I'm just sort of going to arrange these. Flow directions going to be on top. It's sort of funny, you know, it's this visual tool and you can just drag things all around. And you do, especially if you try to build a more complex model in here, you do have to do your best to keep things organized because they will get a little crazy. So these are all the inputs we need. So let's click over to the algorithms here. The first thing we're going to do is run the r.watershed tool. I'm just going to search for it. Oh, sorry, not the r.watershed tool, the r.water outlet tool. We've already run r.watershed, and there's no reason to include the r.watershed tool in this model because we only have to run r.watershed once, and then we're just using the flow direction raster, which is one of the outputs from it. We'll use that every time we run this tool. In fact, we'll use it twice every time we run this tool. So I'm going to double click on r.water.outlet over here, and it is going to ask me, firstly, what I want to call it. It's sort of important to name things to give things descriptive names because you can really lose track of what's what in these models. So I'm going to call this watershed of upper reach point. And so what's the input raster map? Remember that the r.water.outlet tool needs the flow direction raster. So if I just click here, there's the flow direction raster. If I give it that, it just refers to that specific raster that's in my workspace. That would work, but it sort of makes the tool a little bit brittle, and it makes it really specific to this one, QGIS project that I'm working in. So instead, I want it to ask the user what the flow direction raster is, and then use that. And so I already identified that as one of the inputs. So I'm going to click here on the little number icon, and I'm going to say this raster map comes from an input to the model. So I click on model input here, and there's only one raster. So there's only one raster as an input to this whole model. So there's only one thing it possibly could be. And then the coordinates of the point. So same thing. I don't want to just enter coordinates and have them fixed. I want it to use one of the inputs to the model. We said this is the upper reach point. Okay. And then the output, I'm not going to give the output a name because it's not the output of the whole model. It's just a temporary result along the way here. And in fact, one of the advantages of this graphical modeler is that all the intermediate outputs, they don't end up clogging up my workspace. I only get the final output that I want. Okay, so Um, we have this watershed of upper reach point, which is the r.water.outlet tool. And we can see it depends. These lines are showing us the dependencies. We can see it depends upon the flow direction master and the upper end of the target reach. Okay, so the next thing we want to do is we want to take the output of that and we want to turn it into a vector. And polygon, how about polygon? Polygonize. And so the tool under GDAL is the one I recommend. Polygonize raster to vector. And for the input layer, now we're doing something different here. The input layer isn't just a layer that's in my workspace, and it isn't one of the inputs to the model. It's actually the output of this tool right here. So I'm going to say algorithm output. And well, there was only one option because there's only one algorithm that we've configured here. That's all I need to do here. Again, this is not my final output from the model, so I don't need to do anything else. We're ignoring this dependencies field because we're able to tell this layer which layers it depends on, or sorry, because we're able to tell this tool which layers it depends on. The GIS can actually, the software can go through and figure out in what order to run the various tools. And so you can use this dependencies thing to tell the software specifically what tools depend upon what other tools. But in this case, because we're using the output from one tool as the input for another tool, it's clear. Okay, so, oh, I should give this a better name. Let's call this make upper, I don't know why I'm capitalizing it, upper reach watershed vector. Okay. Okay, so now I want to do the exact same thing for the lower end of the reach. So I could just go through that same process, but it's actually even easier. I'm just going to grab these two, just Control C to copy them, click off of it, and Control V to paste them. Okay, they ended up over there, move them back. And so now I just got to go through these tools and point them to the right input here. So this one used to be called, where I copied it from, it was watershed of the upper reach point, but now it's the lower. And instead of using the model input for the upper end of the target reach, it uses the lower end, of course. Okay. Same thing here, used to be upper, now it's lower. And instead of using the algorithm output from watershed of upper reach point, now it refers to watershed of lower reach point. And so you'll see that the names that I gave these tools are pretty important because if they were both just called r.water.outlet, which was their default name, well, I'd have two options here and they'd both say basin from algorithm r.water.outlet, and I would have no idea which was which. So lower, lower, we're good. Okay. So now we have two vectors, one of which represents the upper area and one of which represents the lower area. And so, of course, we just need to find the difference. So here's the same vector overlay tool. We used it in the last module. Oh, I can never remember which layer is supposed to be the input layer and which layer is supposed to be the overlay layer. But in case you haven't figured this out yet, there's a help button down here. And oh, it doesn't work. That's nice. Okay. Well, let's just ask Google. Normally it should bring up the oh dear. Normally it should bring up the QGIS help website specific to that tool. I think it doesn't work from within the model builder, perhaps. But QGIS vector difference. Um, no, I don't want a video. There we go. This is the help button's quite nice when it works. Um, Vector overlay, difference. Okay, difference extracts features from the input layer that don't fall in with the boundaries of the overlay layer. So features from the input that are outside of the overlay. So we want input to be the lower point and overlay to be the upper point. That way, what we'll get out of it is the portion of the input that is not within the overlay. So the portion of the lower that's not within the upper. So go back to the model designer and back to this tool. So what did I just say? I said we want input to be the bottom. So again, this is an algorithm output, and I want it to be the vectorized result from make lower reach watershed vector. And then the overlay layer, another algorithm output, is the upper. Yep. Okay. And then this is the final result. This is all we're doing with this model. So I will name this reach specific watershed. Okay. Um, and that's the only difference tool, so I'm not going to worry about giving it a name. Okay, so this is my complete model. Let's see if it works. In order to save it, we have to give the model a name. I'm going to call it Reach Watershed Creator 3000, just to make sure everyone knows it's extra fancy. So I gave it a name there. I'm going to save it. Oh dear, I'm on the virtual machine, so none of this makes any sense. Oh, good. We'll put it in there. It's the name we put here in model properties is the name it appears under, and the name here is the actual file name. It's sort of confusing that those are different, but they are. So reach watershed analyzer. Good enough. Okay, model was saved, and then I'm going to click this green button too, which says Save Model in Project. Um, that will, that's just a little shortcut that will make it visible in the project. Okay, so I'm confident it was saved. I can always open it again and come edit it if I need, but I think I got it right. So I'm going to close this graphical modeler window and go back to my main QGIS window. And let's see how we did. So down here under project models, this popped up. And here is the Reach Watershed Creator 3000. Excellent. Okay. So I open it, and just as I wanted, it asked me for three things. Firstly, what's the flow direction raster? It's flow direction. What's the lower end? And these points you just define them by clicking on them. So click the three dots over here, and then let's just go click on the lower end. I'm just sort of testing it out here. Okay, there's a lower end. There's an upper end. Something like that. Okay, we'll just let it produce a temporary layer. Click run. So it's got to run that R water outlet tool a couple times, and then turn things into vectors and calculate a difference. Doesn't take too long. And there we go. That's pretty convincing. So that's the watershed. If I move the streams layer to the top, that is the watershed that is that drains specifically to the reach that is defined by the bottom point where I clicked and the top point where I clicked. Um, and I don't have to respect um, the definition of stream segments that came out of this, or the identity of stream segments that came out of this, the r.watershed tool. For example, I can click above and below tributary junctions. Let's say I'm really interested in, oh, sorry, scrolling is a little slow. I'm really interested in changes in water quality that occur, across this whole section here of, I think this is the North Fork of the West Fork now. Um, so you do have to be careful to click on one of the stream pixels. So that was the lower end, and then the upper end. So we're skipping across a bunch of different tributary junctions, but again, that's no problem because we're calculating those basins fresh. We're not depending on the basins that were calculated from the r.watershed tool. So if I zoom out, yeah, there we go. So that's the whole, in this case, quite large contributing area associated with the reach defined by those points I clicked on. Okay, so we built the Reach Watershed Creator 3000. It's actually pretty quick. I will say that's about the optimum level of complexity for something in the graphical modeler. You can get fancy with it. Sometimes you get lucky and it works as you intended, but in my experience, more often than not, if you try to get too fancy with the graphical modeler, you end up having a bad time. And we're trying to minimize that here. Anyway, but we combined, I mean, a total of, if you count both paths there, we combined a total of 5 or 6 steps into just one simple tool, and it runs quickly and it's easy to understand. And it lets us run this anywhere in the watershed. And it's the sort of tool, I will say, you can save and distribute these tools, and so you could share this tool with anyone, and as long as they had a flow direction layer, and as long as they were careful to click on streams, well, they could apply this tool themselves without having any understanding of the fancy GIS work that's going on in the background. Okay, so I'll pause the video, but just to give you a little bit of a preview, we're going to do a little bit of an analysis of the national land cover data set. We're going to look at the change in land cover types that's happened across this whole watershed. And then we're going to, of course, come back to this tool that we just built, and we're going to use it to click around and take a look at that change for a couple of reaches specifically. Okay, let me figure out how to pause the recording. All right, so I'll jump in. I'll jump into the next video, and we'll think a little bit about the National Land Cover data set.